You're listening to Wurth Electronics What's Up Radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and our very own Wurth Electronic technical specialists. We're going to shine a light on interesting topics such as energy harvesting, wireless power transfer, EMI issues, along with so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Wurth Electronics What's Up podcast. In today's podcast, we'll introduce you to the world of surface mount ferrites and also give you an insight into the production process with our popular webinar, Small, Inconspicuous, and Underestimated. EMC Ferrites are more than only birdseed on the PCB. Presenting this topic is Joanne Wu, Product Manager for EMC PCB Ferrites at Wurth Electronic. In this presentation, Joanne will show the influence of DC bias and also explain the differences between the old measurement type and our new extended measurement type. She'll also discuss the influence of temperature and compare the WE-CBF surface mount ferrite to the WE-CBF HF, which is our surface mount ferrite for high-frequency applications. We'll then finish up with the pulse current detection of the WE-MPSB and the new pulse definition of wired surface mount products. Enjoy today's Wurth Electronic What's Up podcast with Joanne Wu and our presentation, Small, Inconspicuous, and Underestimated. EMC Ferrites are more than only birdseed on the PCB.
It seems that ferrite beads are quite big. However, there's a trick. And we've used a mini dies, so technically the PCBs aren't as big as you think. In today's overview, I'll do a quick basic introduction, then I'll move on to high-frequency ferrite beads, then an overview of the production process, to further on the influence, like DC bias and temperature, affect the ferrite bead in application, and lastly, to conclude, a pulse current definition for Inrush Currents. As we all know, there are two different types of EMI problems. Ones that are received, conducted through, for example, power supplies, cables, and another one that is radiated out of our application device. In general, SMD ferrites are suited for radiated emissions. As we can see here, this is a radiated emissions test, and there are different limits that we need to comply. This one here is shown for an industry standard. The emissions here are over the standard, and there are different ways to solve EMI problems. One way is to use a ferrite bead to smooth out the noises. And here is one where we've used a ferrite bead, which then they pass the test. So, on to the basics. Ferrite material. What is a ferrite material? Ferrite is part of the ceramic family. It's an inorganic material and multicrystalline. This means that a ferrite is quite hard in structure. However, if you drop your PCB or if you drop a ferrite ring core in general, you can see that they break easily. That's because they are brittle. Ferrite material is based out of nickel zinc or manganese zinc, however mostly nickel zinc, and it has the ferrite component or ferrite iron oxide component, which everybody knows more or less as rust. The characteristics of a ferrite: it is just a passive device. It's like an inductor. However, instead of storing the energy, here you want to remove this energy in the form of heat. The electrical properties depend on which frequency range you are working in, and the material, and which I've mentioned before, nickel zinc or manganese zinc. One main electrical property that we see for ferrites is the impedance. We know that they are categorized, is made up of the real part here and the inductive part, positive or negative. This is a typical impedance curve from one of our data sheets. We show 3 curves: the impedance, the reactance, and the resistive part. In the first part, in the low frequency region, the bead acts more inductive. In the green area, it reacts more resistive. So this is where the self-resonant frequency is. And when it comes down, the ferrite bead reacts more capacitive. As the main function of the ferrite bead is to dissipate the noise, we would treat it more like a resistor and use it within this region up here. Following is the construction or the structure of the ferrite bead. It has a main ferrite body core with silver layers, printed layers. Mainly there are 2 types. One here, which is a vertical winding from terminal to terminal, and the other is a horizontal winding. So starts from one side and coils up and ends on the other side. This here we called as a standard structure, and this on the left we categorize as a high frequency structure. So here's a 3D model to better show the layers, the inner layers. But how does the structure relate? How does the structure relate to the classification of high frequency and standard? As we can see in this diagram here, the capacitors or the parasitic capacitance is within the internal layers from one terminal to the other. This here we call is summed up in series. In the standard one, the parasitic capacitance are from terminal to inner layer back to terminal, and so on. And here when we sum it up, they are in parallel. As we can see from this vector diagram, when you have less capacitance, you have a smaller decrease in the imaginary field. And with more capacitance, obviously lower. So when we take the magnitude of the impedance, your Z would be higher when you have smaller capacitors. This can be seen in the impedance curve, where typically if you take the tip of the SRF point, they are shifted nearly by a decade. We have an application note coming soon that will feature the differences between high frequency and standard. So an insight into the production process. Firstly, we have ferrite powder and binding material. This is mixed together. Then we go through a ball milling, which makes the particle or grain size smaller. Then we tape cast, we fill out the ferrite paste, and it goes through a printing process. After the printing process, it goes into lamination. Lamination's where you compress all the layers together. Afterwards is a cutting process where you dice up each panel into your chip beads. After cutting is a burnout. This phase is where we try to burn out all the binding material that was added at the start because it's not part of the ferrite. It's not needed. This is also another reason why the chip bead ferrites don't have a UL certification. It's not required since all the flammable material has already been taken out of the component. After the burnout phase is sintering, where it goes through the oven. Then each part is then tumbled. Tumbling is to smooth out the edges. Termination happens to dip both sides of the chip bead to make a connection. Then it goes through the oven again. Then plating, where you put on layers for your soldering. And that is the completion of a ferrite, a multi-layer ferrite. Then it goes through sorting, which you look at the electrical specs to make sure they're qualified, and appearance, how does it look? And lastly, they all go into a reel. So I've highlighted here 4 boxes, which we will have a look into the process. Mesh printing. First, you would calibrate all your devices, so to make sure that all the meshes match up in line with the panels. This is a mesh board where you can see little white cutouts. So this stencil would be where all the silver layers be printed on. In the last clip here is the ferrite printing. This is when the ferrite paste is put on and rotated to get each winding, to get your coil windings. Yeah. The electroplating of nickel and tin is the dipping after you've done your termination. You have your ferrite core, then we add on a silver layer, or sometimes mixed with glass. Then there's a nickel layer. Nickel layer is good for making sure that you have no tin whiskers. And lastly, you have a matte layer, and that finishes your termination. Here they go into different barrels of different pools of chemicals for each of these layers. Electrical sorting happens in a big ring where each components are sorted out and they are tested here. So there are little slots which each part is measured to make sure that they fit into specification, and afterwards are sorted into different categories. It is then gone through an AOI, which is automatic optical inspection. Here we use different colors, different LEDs to make sure the visual looks, the physical looks of a PCB. Of a PCB ferrite. And anything that looks different, strange, is automatically taken out. Onto a measurement topic is the rated current. So this is a typical setup of an impedance to measure the impedance using an impedance analyzer. Here there are 2 fixtures. This fixture here can go up to 3 gigahertz plus a DC bias adapter to put in your DC bias current. However, as you can see that this DC bias adapter is limited up to 5 amps. All our datasheet information we can only show up to 5 amps. This is the same situation with the impedance, so everything is up to 3. Hence, now we have made a new measurement setup where we can measure up to 20 amps DC bias is possible and up to 8 gigahertz. At the same time, we try and reproduce the reality of a chip being used on a PCB. Here is an example where we measure up to 8 gigahertz and the capability of this part up to 10 amps. For the temperature, different materials have different Curie temperatures. In this case, you can see that when you go above the Curie temperature of a chip bead ferrite, it will then go into a saturation mode. This is where the permeability of the ferrite is close to 1, which is close to air. That means the ferrite will no longer work as a ferrite. For the temperature, we do measurements from minus 55 degrees to 160 degrees. In our data sheet, we specify it at room temperature. Here is an example of 3 different materials. The first material has a Curie temperature less than 130 degrees. This is where you can see that at 160 degrees, it's saturated so much that it no longer looks like the original impedance curve. At Curie temperatures of greater than 130, so roughly around 180 or so, the saturation is much better. It's closer to its original. And with Curie temperatures much further away at more than 180, which is usually at 220 degrees, it's just a drop at your resonance frequency. A last topic is about inrush currents. So for the inrush current, usually when your capacitor charges up very fast and discharges, you get a possibility of high peak currents. This is when you think, okay, is ferrite able to handle it? It is easy to destroy a part, as you can see in this photo where they crack usually within the silver layers, or they shatter here, or at the end terminals. However, there are different types of ways you can withstand. You can add a capacitor at the start to avoid peak currents to destroy your part, or you can design in an SMD ferrite. However, it can only go up to the maximum rated current. If you have situations where you're using large main powers up to 100 amps, then it's best to substitute with wired ferrites. We have one particular series called the WE-MPSB, where we have a new definition, not just the usual rated current. There is a specific MPSB specification that we make sure it can handle these inrush currents. From this chart, we test a pulse length of 8 milliseconds at 100 amps. And as you can see, depending on part, let's just take, for example, this black one. At 8 milliseconds, it's still able to put in 25 amps. When you have even lower, then it can withstand a much higher current. We also test the number of pulses, so 10 pulses per 8 milliseconds. And lastly, we have a new pulse definition for the PBF series. This definition is a new setup where we try the pulse duration of 1 millisecond, and the condition is when the part is running at room temperature until a difference of 40 Kelvin. Usually we can see that at 1,000 milliseconds, so 1 second, most PBFs here can take at least 40 amps in current.
This podcast was taken from an updated Wurth Electronic webinar. To view our materials and replay the webinar on demand, visit our website at www.we-online.com/webinars or click the link attached in this podcast. You can learn more about ferrites with our previous What's Up podcast episode, Ferrites for Ringing Control. Look for this episode in our profile or click the link available in this podcast. You're listening to Wurth Electronics What's Up Radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Wurth Electronic technical specialists. We're going to shine a light on interesting topics such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Wurth Electronics What's Up podcast.